We're so glad you could join us. We have an amazing presentation from Katie Salamati talking about flood preparedness. Across the Southeast, we've seen a lot of crazy things happen with flood over the last few years, and she's got an amazing presentation to tell you about what SAS is doing about it. And before I get into too much detail, Katie, take it away.
Thank you. Can you all hear me? Okay, great. Well, thank you everyone for being here. My name is Katie Salamati. I'm a principal industry consultant with our IoT division, and I'm here to talk to you about our flood solution. This is a solution that we've been working on at SAS for the past couple of years now. We have great active customers, and we're trying to help them prepare for flood events and be able to be more proactive and actually save lives. So why we are starting with flooding, and essentially because flooding is one of the most common natural disasters that are causing human lives and are causing a lot of damages. It's 1 in 4 people are at risk of flooding. As I mentioned, is the #1 most frequent natural event that we're experiencing. And the past couple of years, the cost of flooding has been about, the damage that it causes has been about $180 billion. So it's definitely something that needs a lot of attention. When it comes to flooding, what are the challenges? It definitely is a threat to human lives and properties. It impacts work, it impacts economics of the cities, towns, and even states that are hit by floods. It is a global problem. It's not only to the United States. It's not only for urban areas. It's not only for states and cities that have rivers flowing. It's a common problem for everywhere. 99% of the counties in the United States have been impacted by flooding in the past couple of years. And also, when it comes to flooding, even though there has been years and years of engineering happening, we have flood mapping, we have hydraulic engineering happening, it's still a problem that is facing lack of resources and lack of essentially preparedness and awareness. So it's something that we hope that we can predict, prepare, and better respond to flooding events for communities and for saving human lives and properties with the SAS flood solution. So what is the SAS flood solution? The purpose of the SAS flood solution is to be able to protect human lives, being able to better respond to flood events in advance before these flood events are happening. So being able to better predict that and organize the resources and organize the right accommodations for better responding to flood events when they happen, because they're going to happen anyway. This is a natural disaster. It's going to happen. There's nothing that we can avoid it, but how we can better respond to that and prepare for it. And also over time, how we can improve that. And there are many ways that we can improve responding to flood events and avoid flooding. Many of the floodings are happening because of developments that are happening because we are paving the roads, we are taking out vegetation, we are taking out trees that might be stopping the floods, we are changing the soil structure, and so how we can over time better improve our response to flooding and better improve the environment so we can control these flood events with minimal damage. Again, minimal damage. We can never bring that to zero. So the SAS flood solution has many components and capabilities to that, which I get deeper into this, but it covers from this is an IoT solution. So essentially involves a lot of real-time data, sensor data, is a cloud approach solution. And with these different components that we have, we are monitoring the health of the sensors and the hardware that are providing us real-time data. We're doing historical analysis of what has happened in the past, so then we can better be prepared and predict the future. We're doing current condition monitoring of what is happening right now, and also better predicting of what is going to happen. In addition to that, you heard about digital twins this morning. So Flood Solution is one of our very first digital twin products that are out there. And you might have heard Brian Harris said, what if we want to test what if? And that's exactly what we're doing with the Flood Solution. We're trying to test and do what if scenario analysis of what if we are changing the pavement structure, what if we are adding vegetation, what if we are changing the elevation of the roadways because of construction happening, how is that going to impact the flood? What if we know there's going to be a flood, but then we put in a water pump somewhere, we're closing the road so people won't travel that way, so we're saving lives. So we have the capability to test all of these different scenarios. So you might have heard about digital twin. I would say with the flood solution, we're essentially creating a digital twin of water movement as it rains, as it floods in the city, in the environment that we're simulating. So then we can test different scenarios, we can predict, and we can better prepare for flood events. When it comes to flood events, usually people would think that, okay, if it floods, it's the river that first is going to be flooded and then it's going to inundate the land. But actually with the urban flooding, that's not exactly the case. Sometimes we have the environment that is first flooded because they might be at the lower elevation of the river. So creating this digital twin and understanding the different components of the flood event is a bit more sophisticated than just imagining that it's the river that is going to be first flooded and inundating the road. So how we're doing this with our digital twin capability. The flood solution has many different layers of information and data that are coming on top of each other. It starts from water level elevations or earth elevation. Then we're adding layers of soil infiltration, flow resistance, runoff due to impervious areas. So we are factoring in what the percentage of impervious areas that we have for our region of interest, and that would be the percentage of, for example, the pavements, the parking lots that we have. Then we are also factoring in the storm inlet capacity systems. We are bringing in precipitation and weather forecasts and rain forecasts. We are adding in sensor data for real-time awareness and real-time understanding of the environment. So we're creating all these layers on top of each other to be able to simulate and predict the flood event. And so our flood model, what we call it, is more of a rain over grid flood model. It's actually one of the highest fidelity flood models that are out there. And the way that it works is that we create a grid of the cell sizes of 250 feet by 250 feet. Our closest competitors' grid sizes are 8,000 feet by 8,000 feet. So we go very granular. We can actually have the capability to go down up to 50 feet by 50 feet. So essentially by your house level, you're able to see if my house is going to be flooded or not. And so we're creating these grid sizes or cell sizes of the grid, and all these layers of data and information that I talked about, they're layered over on top of this at this grid structure and this cell size of the 250 feet by 250 feet. So we are adding all that information. We are adding in real-time sensor data, and we're essentially predicting where it's going to be flooded, how much the land is going to be inundated, what the water levels are going to be, and providing that real-time information and prediction. And also in addition to that, we're also providing alerts that would provide where it's going to be flooded and how much. So the model, the basis of the model works as we call it, as a digital elevation model. So the grid sizes, or the grid model that I mentioned, the rain over grid model, looks at the elevation of each of these cell sizes, the 250 feet by 250 feet cell sizes. And then we simulate every 30 seconds based on what is happening, the real-time information that are coming from the sensors. And based on the predictions, the weather predictions, we're not doing the weather prediction. That's for someone else who does it. But we bring in those weather predictions into our model. And essentially every 30 seconds, we are running these cells, simulation for each of these cells of how the water is moving from one cell, 250 feet by 250 feet cell, to another. And every 30 seconds, as the real-time data is coming in of what the ground is, how much the water is looking at with the sensors that are stream gauges, water level sensors, at the rural level, urban level, coastal level, or even ravines, we're bringing in all this information, and then we're simulating and running this model. So if you know VIA, you know that productivity really matters here and how fast we can run these models. And the reason that we can be very granular is because these are massive amounts of models that are running. Every sensor that are installed in the environment to provide the data, they have their own machine learning model to predict what the water levels are going to be. And so essentially, we're running sometimes thousands and thousands of models. These models need to do prediction in time because these predictions are happening. The alerts are going out every hour. So for example, at our 11 a.m., I have a prediction for 12 p.m., 1 p.m., 2 p.m., 3 p.m., 4 p.m., 5 p.m. And so my prediction of 1 p.m. needs to feed the prediction for 2 p.m., for 3 p.m. So essentially, if you're looking at a very large area and we have these thousands of models, we need to run them under an hour, which is we are using VIA. So that's why we have that productivity and we can run that fast. So we are using these, running these models in time to be able to feed the predictions for the next couple of hours. So when I say we are providing predictions for 6 hours in advance of what the inundation is going to be and what the water levels are going to be, is because we are running these models frequently and we have to run them in time. And that's why our competitors have not been able to do that, because we build the architecture in a way that can support these predictions and can support these machine learning models. And in terms of the data that goes into that, there are various data sources that feeds these flood models from the historical data. So there are lots of engineering that happens, many years of engineering with the flood maps, with the hydrology data, with the storm and flood data. So these feeds into the model. Then we have the physical data, the 2D mapping, 3D mapping, topography, SAR data, and all of that. So combining these, we're doing the flood simulation. In addition, we have the sensor data, the rain gauges, the depth and flow, the soil composition, tidal height, any of those, any type of, imagine civil engineering related, hydrology, water related sensors that are available. We can leverage that. In addition to that, we actually have an IP on where would be the optimal location of these sensors. So when we're working with a client, we're not recommending that you have to put in sensor at every cell size. You don't need to cover all the areas. We have an optimization model that identifies the optimal location of the sensors and the minimal number of the sensors that are required to cover the area and to provide the right amount of information. And then we combine that with the digital data, the weather APIs that are providing what the precipitation is going to be, what the rain is going to be, and other third-party systems that are available. So with that, we're creating the ground truth, because the sensors are sending us real-time information. And essentially, it's a combination of a physics-based modeling and an analytical-based modeling that are brought together to provide us with the most comprehensive solution that creates this flood prediction and preparedness. In addition to that, with the digital twin capability, we have the ability to test the what if of each of these inputs to the model. So what if I'm bringing in the weather APIs, but what if the actual rain is going to be more than what the weather forecast is going to be? A lot of the times with the floodings, we know there's going to be flooding, but we're still surprised with the results. We're still surprised that the area was flooded, that we weren't expecting it to be flooded. We're still surprised that this road got flooded or the water level was more than what we expected. So we know it's flooding, but we have still these challenges. And so really, the SaaS flood solution is trying to be able to provide the decision makers with the capability to test these different scenarios. So what if my storm inlet system, some of the inlets are blocked because of a residual water that I have from past flooding events, because of clogs in the system? What if actually my capacity is less than what I expect it to be? How is that going to impact a flood? What if the percent of impervious area, the massive development that happened, the past 6 months over that particular location is changing the water routes, and so they're not actually going to go down in the soil, but there's going to be runoffs into other locations, into parking lots. How is that going to impact this flood? So these what if scenario analyses are focused on each of these data points that feeds into the flood model. And so the flood engineer, the emergency management director, they can test these different scenarios, and so they can be prepared as much as all these factors that feed into the impact of the flooding. So I talked about the impervious areas, especially development at a large scale, changing the percentage of the impervious areas for a location. I come from Cary, North Carolina, and the past 10 years I can say that the amount of available land in Cary has gone down from maybe 50% to probably under 10% because of the amount of the development that has been happening. There are many cities that are experiencing that. So this is changing the landscape. This is changing the direction of the water runoff. And so we want to be better prepared for these kind of events. Then we also have the land cover. This happens a lot. We are experiencing a lot of flooding after wildfires because of the loss of the vegetation, and the landslides are happening after wildfires. It's ironic, right? You get a wildfire and then you get flooding right after that. Again, because of the impact of the change in vegetation that is impacting the flood. We also have the resistance. The different land covers have different resistance to water flow, and so that also impacts the level of inundation. Which areas would be inundated and how much they would be inundated is heavily impacted by this. Our model takes into account the fact that there are adjustment factors that they take into account what is the land cover and which one of these, how much they would have resistance to the flow of water. Then we also have the soil infiltration rate. So what type of soil is covering that particular area? Different. When you look at a city, especially in urban structures and a combination of urban, suburban that leads into rural areas, there are different soil infiltration rates, and each of that, believe it or not, there are also drastic changes going from one particular area from clay to pavement or others that would impact the flow of water. So all of that are taken into account in the model. And then additionally, we bring in the past storm events. So we can configure the model to look at the past, the current, and the future, and really our capability to even simulate the past storm events, feed that information to the current storm events, and also help that to predict the future storm events have been enabling us to have a more accurate model that is essentially as accurate as the weather forecast, because that's the weak point, and it's something that we can cover all these other factors, but the weather forecast is something that is provided by third party, by the weather channels and weather APIs. So we covered all the other bases. We can be as accurate as is out there. The only one that we do not have any control over is those weather forecasts, but our capability to do that, digital twin, that what if scenario analysis actually covers for that. So we provide that kind of capability. And as I mentioned, it's really, understanding, having those historical analysis of what happened within the past flood events, creating those past casts, feeding that into what we call it nowcast. So with the past cast information and the sensors that are available, and then setting that into what we say nowcast. What is currently happening right now? What kind of conditions I'm facing right now? And then these two are feeding into what we call it the future cast. And those are the forecasts that we have the capability to do 6 to 12 hours in advance, and create these inundation models and water level forecast models that provides the future cast. And so the solution is really bringing all that information together to provide a holistic view of any kind of different flood events. I don't want to overwhelm you with this slide, but essentially this is just an architecture of when we're putting in this flood solution. There are various components to go into that, from a LoRaWAN network for communicating and sending the sensor data in, to this being a cloud-based environment. So there are cloud components in there, and also there are SaaS components. But essentially the architecture here can be leveraged for any kind of additional, the blueprint that we've created can be leveraged for any additional solution as it relates to natural disasters, such as wildfires. And so I briefly talk about the different components of the flood solution, but I wanted to do a bit deeper dive into each of this. So one of the main components is the sensor health monitoring. Because we rely on real-time sensor data in addition to other sources of the data, it's important that our sensors are sending the right information. And specifically when we are dealing with natural disasters, that's very important because the natural disasters also impact the sensors as well. And so we want to make sure that we are getting the right data, the right quality data, otherwise garbage in, garbage out. And so we do have a component that focuses on the sensor health monitoring and to make sure that the sensors are sending the right data. If you're seeing outliers, are they outliers or are they just bad quality data? If the sensor is going down, how can we use, we can use triangulation to use the closest sensors to cover that blind spot. As I mentioned, the next component is more of a historical analysis. So the emergency management department, the hydraulic engineer, the flood engineer can go back and look at the past flood events and see what happened. We predicted this is going to be the water level. We predicted this is going to be the inundation. Did it actually what we predicted? Was it actually what we predicted? Or there was some flaws in that? So they can go back and really do forensic analysis of the historical and past flood events. Then it's obviously the current conditions, the monitoring the current water levels and the sensor reportings, and also the current inundation. And then there are components that focuses on the forecasting. So we're going to forecast the water levels on an hourly basis, and also we're going to forecast the inundation, the land inundation on an hourly basis. We'll be sending alerts on what the latitude, longitude of that location is that is going to be flooded based on different thresholds that are in place. Is it minor flooding, major flooding? Is it an action level? Is it no flooding? All of that, sending the alerts out, and also, as I mentioned, the digital twin capability to be able to test all of these different scenarios. I do wanted to show you a quick demo of what we have here. So this component, this part focuses on sensor health monitoring and showing which sensors are sending the right information, which sensors are out, which sensors, how much they're reporting in. Then we also do the predictions of the water level forecast. So you see in this, we actually follow the USGS standards for reporting on the water levels and reporting on the readings, and also providing forecasts. You see the graphs are color-coded to show if we have no flooding, if we are at an action level, minor flooding, major flooding, and all of that. So all that are provided. And we have the data points, so all these data points are created on hourly, well, they're running every 30 seconds, but then we provide these data points every hour, and all of that are, imagine these 6 data points for every hour are updated also as the new forecasts are updated. Then I would also want to show you more about the inundation simulation that we do. So in this case, you see this is a river flooding. Is actually a past flood event for Vermont that we've created the inundation around it. So this is a fast forward of 6 hours that I wanted to condense it to show you in less than 30 seconds. And essentially, you would see that during the next 6 hours, how much of the land will be inundated. And then the model actually provides alerts for each of these locations with latitude, longitude, and the water levels. This is just another close-up of that solution. We do have others that are showing, what the inundation is going to be, what the land inundation is going to be, and really the point of this is to show, even though we have a river here, but it doesn't mean that always the first area that is going to be inundated is river. We have other areas that is going to be inundated. You see them; they are red, that are not close to the river and they're close to the housing units. Valencia, Spain, last year experienced flooding, major flooding. So Valencia is an urban area that experienced major flooding. And so we were able to go back and look at the information that were just purely publicly available. So with this flood solution, we actually do not need to do a lot of instrumentation. We can work with the existing data sources that are out there and really create this visualization and simulation of what happened, which areas have been inundated. And had they had this solution, this is what we created for them after the fact, because they realized that, oh, we have a flood problem, let's go and find the best flood solution that is out in the market. And so we created this for them. So had they have this solution 6 hours in advance, they would have known that which areas would have been flooded. This is another one that we've created for New York City as well. So again, going back and look at which areas have been flooded. Don't think it's actually showing. And then the last one is showing the town of Cary. And so with this one, you would see that with the flooding that is happening, there are also alerts that is going to show, at hour 5 from now, this is how much the land will be inundated, and the alerts are showing color-coded. So there are various different capabilities that exist in addition to all the dashboards that I've shown with, really looking at the charts and looking at the actual water levels and forecasts. And I do want to talk about a couple of customers that have been using the SAS flood solution. One of them is the Dutch Ministry of Netherlands, or Rijkswaterstaat. They have, Netherlands is below the sea level, so they have been instrumenting their infrastructure with over 2,000 sensors in the dams, in dikes, in roadways, and they're monitoring the information that these sensors are sending in real time. So they're looking at what the outliers are, and essentially with our real-time or streaming AI capabilities, they can flag if there's going to be an outlier, and this outlier is due to a certain flood event that might be happening or a weather event happening. So they can make a decision of, do I need to close this dam? Do I need to open the dam? Do I need to close or open any gate to avoid any roadway structure? So they're taking a very proactive action toward that. Another example is North Carolina Department of Transportation, that they're using using flooding information to better predict what the impact is going to be to the infrastructure, and which infrastructure is at a higher risk of being flooded, and how much the cost of that flooding is going to be. So from a state standpoint, from an agency standpoint, it's very important to understand and plan for how much damage I'm going to experience, because the damage is going to happen anyway. We can avoid the loss of lives, but most of the time we cannot really avoid the loss of damage or the damage to the infrastructure. So how we can avoid that? And then the last one is actually Town of Cary is one of our very first customers, and because they are at the top of one of the top watersheds for the state of North Carolina. And so they tend to get flooded a lot, as I mentioned, with the recent developments that have been happening with the town. The elevation of the town has changed, the percentage of the impervious areas have changed, the soil structure have changed, and so we've been working with them, we've been partnered with them to better predict and forecast which areas would be flooded and how much they're experiencing inundation. I don't know, and that's it. So I appreciate your time. I'm open to any questions if you have. I don't know, Peyton, if there's time for a question. Thank you so much,
Katie. Let's everyone give it up for Katie one more time. Amazing presentation, very pertinent, especially in these times. We appreciate you all stopping by. We're gonna have another presentation coming in the next 10 minutes. Stay tuned, stay tight. I hope you guys have a great rest of your day.